Hello, this is part 4 in a little series I'm calling Principal Components. This one I'm titling Correlation, where we look at the correlation between principal components and the original variables. We also standardize the variables too. So throughout the video, let's let X be a 1 by P vector, or you could think of it as P variables, with the variance covariance matrix sigma. Let the lambda 1 E1 through lambda P EP be the eigenvalue vectors of sigma, with lambda 1 being the largest, lambda 2 being the smallest. And let's let Y1 be the first principal component, YP be the pth principal component. And I already see an error. So, in earlier videos, we showed that the variance of the principal components is just the lambda, or the eigenvalue associated with it. The covariance between any two principal components is 0. So here, now the magnitude of the components. So notice that, so the first principal component is a linear combination of the x's. And this eigenvector is normalized, so it has a length of 1. But what that does is it helps us know the bigger in magnitude these are in absolute value, the more important that variable is in contributing to that principal component. So the ith eigenvalue is this, and then we look at the values or the magnitudes of these components, and it measures the importance of a variable to that principal component. So again, the yi is equal to EIX, and then it ends up being this. And so if these are if a coefficient's relatively small, then it says that variable doesn't contribute much to that first, the principal component. If it's large, then it's big. And matter of fact, note that the component, or the EIJ, is proportional to the correlation between that principal component and the jth observation. And that leads to our next theorem. The correlation of the ith principal component and the jth variable is this. And notice that's that coefficient in front of the or for the eigenvalue, or for the principal component. So let's let Lj be a vector of all zeros except for 1, 1 in the jth component. And that's such that xj is equal to this. So when we take this linear combination, since it's mainly zeros, all of them drop out except for that jth component, which is what this is. Now the covariance between xj and yi, so this is the jth variable, the ith principal component. Notice it's the covariance, not the correlation, is equal to this. So we replace xj with this linear combination, and we replace the ith principal component with this, and that allows us to take those vectors out front and then transpose it out back, and that's what we get here. And it's the variance of x, which is sigma, but this is an eigenvector to sigma, so that we can replace sigma with lambda I, and since it's constant, take it out front. Well, then this is all zeros except for the jth component, so when we do this vector product, we just get the jth component of that eigenvector. Now, putting all the pieces together, the correlation between the jth component and the ith principal component is this: the covariance divided by the standard deviations. And the covariance, we said, was this, and the variance of the ith principal component is lambda I, the variance of xj is sigma jj. So then this simplifies to this, and the result is true. Now, one note here, standardizing the x variables. And what that means is subtracting the mean and dividing by the standard deviation. So this is recommended if the variables are not measured on the same scale, or at least one of the x's has a much larger variance than the other x's. So not measured on the same scale, let's say it's your annual income versus, how tall you are versus, your, some other variable. And so they're not measured on the same scale. And so the variances associated with them aren't really comparable. So what you do is you standardize the variables, your x's, and then you run principal components on those standard variables, standardized variables. And the same way, if one of the variances is much larger, so say all your variances around 1 or 2, and then your 10th variable has a variance of 100, well, that variable is going to dominate the the variance associated with all your data. So it's going to be associated with, a principal component, and it might not be the smartest thing to do. So what we do is we standardize the variables. So we subtract the mean from each and then divide it by the standard deviation. And we come up with these Z's, Z1 through ZP. Now, the Z's, we just act like they're the new X's. So we do everything we did before, but with the Z's instead of the X's. So in matrix notation, this becomes, it's a vector of X's minus their respective means divided by the standard deviation. And so this is a diagonal matrix, with the standard deviations down the diagonal. And so this produces a vector of these. So now the expected value of Z is 0. The variance of Z, you can take that out front, take it out back, and it's a variance of this. Adding or subtracting a constant doesn't change the variance, so that's just sigma. And then when you divide by the standard deviations everywhere, it ends up being a correlation matrix. So this is, well, let's put it here. So this is ones down the diagonal, and this is the correlation between any two variables. So it's symmetric. This is equal to the top half is equal to the bottom half. And, because this is, full of covariances, and then when you divide it by the respective standard deviations, you get correlations. So now let's let V1 through VP be the eigenvectors of rho. And I tried to really make, it's kind of standard to call it rho, but when I write a rho and write the letter P, they look similar. So I really tried to make that diagonal to make it look like a rho, the Greek letter. So the V's are going to be the eigenvectors associated with the variance of the Z's. Then the principal components are just, and I put a star that means that the variables have been standardized. So it's the first eigenvector times our vector Z, The pth component is the pth eigenvector multiplied by Z. Now, we could write it like this. Z is technically, in matrix form this. So we could write the principal component is this, where V is the eigenvector associated with the correlation matrix, rho. And it should be noted that in general, the principal components from sigma are not the same principal components derived from rho. Using part 3, the results are very, we can go through these results. The variance, actually this is the total variance. The sum of the principal components is equal to the sum of the variance of the ZI's, which is P, right? Each one of these has been standardized to have a variance of 1, and then we're summing 1 from 1 to P, so it's P. Now the covariance between the ith standardized principal component and the standardized variable is we can replace what they are in here, and then we can take that vector out and transpose it out back, and we get this. And this is rho. The variance of Z is the correlation matrix, but VI prime rho these are eigenvectors associated with this, so we can just stick in lambda I and pull it out front, assuming that's the eigenvalue associated with that eigenvector. And maybe I should have used something besides lambda. Now this is, remember this is a vector of all ones right here, except for a vector of all zeros except for a 1 in the kth spot. And that's how we get this back. And then so when we take this vector product, we get the kth component of that eigenvector. Okay, so that's the covariance. The variance, as we said, of zk is 1. So now the variance of the yi's is the variance of the eigenvector times z. And then we can pull this out and then transpose it out back, and then it's the variance of z, which is rho. But this is an eigenvector to that, so we can replace that with lambda I, and since it's constant, pull it out front. But these are normalized eigenvectors, so the variance is lambda I. The correlation between the ith standardized principal component and the kth standardized variable is, this is the formula, and then plugging in what we have up here, it's this. So the coefficient of that eigenvector actually tells us a lot about the correlation between the ith principal component and the kth random variable. The proportion explained by the standardized principal components is this. So for each k, so this is the variance associated with an eigenvalue, and the total population variance we said was p. So this is the proportion of the variance associated with the kth standardized eigenvalue. And then of course we want the first, so many eigenvalues to account for so much of the variance, and etc. Yep. Well, anyway, that's all I have for today. Hopefully you enjoyed that. This is probably my last video on principal components. I was going to do a couple more videos on the statistics of this. So these are population parameters, and in practice we do not usually know the population parameters, so we substitute in the sample statistics. But then there's a sampling distribution associated with say the sample principal component, or the sample eigenvalues, sample eigenvalue. And then there's some distributional properties, and we can create confidence intervals. I was going to do that, but it ends up this series is really not being watched much, so I'm going to stop. And if you want me to proceed to that, make a comment. And otherwise I'm moving on to a new topic. Talk to you later. Thanks. Bye.